Hello, this is Don Mitchell, and we have Tim Chambers here as well. This is today's presentation is a continuation from yesterday, where Tim and I spoke on what he has done as CEO of Cool DC, a data center that's dedicated to energy efficient application of liquids and IT cooling. And my background is between the two of us, we have about 50 years of cooling data center experience. Myself started with APC, went on to Schneider, and today I work with Victaulic on the liquid distribution in data centers. And ultimately, that will be the final point of today's discussion. But we'll start out with the overall agenda. And the agenda, we're going to look at the high density data center facility challenges. What is causing challenges in our data centers today? Liquid cooling opportunities. We're going to kind of review some of the things that Tim mentioned yesterday, but from a slightly different perspective. We're going to look at the types of liquid cooling from the ASHRAE perspective. We're going to look at energy opportunities from the green grid perspective, not only of optimizing what we call PUE, but also the concept that energy is neither created nor destroyed. Data centers don't consume any energy. Data centers don't consume any energy. They convert electrical energy into heat energy. That energy can be reused with proper technology, and liquids enable that at a much greater level than air-cooled does. And we're also going to look at the key focus of today's discussion as we come back to, if we agree that liquid is the right answer or is a good answer, how do we make it the installation simple, adaptable, and reliable? Kind of jumping to this first, the title of today's presentation was How Many Barbecues Fit in a Data Center? And where did that title come from? It came from the fact that very few people understand kW as a measure of heat. But they do understand barbecues as a measure of heat. When I heard one of these presentations in the past, I actually went on outside and I bought a Weber 3-burner barbecue, and I found that that barbecue put out exactly the same amount of heat as one 10 kW rack. So I started talking in terms of barbecues, because I think that is a term that more people understand than kW of heat. As we start looking at the world of liquid cooling, some people think that's a new concept, but ASHRAE TC 9.9 has already sent over decades looking at liquid cooling. They've defined liquid cooling types, and to the extent that the Open Compute project wants to move forward, they should look at some of the references that have come out from ASHRAE when you start talking about liquid cooling types being liquid cooled rear door rack and rear door, liquid cooled IT, liquid cooled electronics, and immersion and single phase. And they've also defined sources. So in terms of terms and testing, ASHRAE already has a lot of foundation there. Tim, why don't you kind of run through, as we start looking at those terms that I mentioned before, just a brief comment on which technologies inhabit your data center and any other things you'd like to add.
Right, so what we've got on here is what we call water cool type cooling, where we're actually using in-row coolers on the left using an OTAL containment. So effectively the IT goes in the middle, the in-row coolers pull them all out and then blow the cold air out. What you've also got the side of that then is the rear door. So the rear door is the idea where the rear door is like a big radiator at the back, which effectively pulls all the heat out the back of the IT and dries it front to rear. So in both of these cases, it's actually a water-based solution that works. If we now go back onto the next slide and we go on to liquid cooling, where this one works, this is where we're physically actually using a different type of liquid. Some will always say things like it's like using things like baby oil, and effectively that's what it does feel like. But effectively what you're using is a non-motor based liquid where you're physically immersing or placing onto the IT liquid to do the cooling. So if you take the ones on the left, you've got the single phase and the two phase, where you're actually using liquid physically on the chips. These chips get hot, they take it down through pipes back out into the main heat exchange. If we then go on to the right, this is where we call immersion cooling. So this is physically where all the actual server card is actually physically dropped into this liquid, and then using natural convention or pumps in some cases, the heat is then pushed out and back into a heat exchanger.
Great. So what's the point here in terms of how are we impacting the world of energy usage? And I touched on this briefly, but liquids have a much greater opportunity to optimize your PUE, especially as your density and diversity of your density increases. Um, the cascade cooling was a topic that Tim talked about yesterday, and we're going to talk a little bit more about today. The ability to take the rejection temperature from a computer room air handler or air-cooled unit item and actually use that as the supply temperature for cold plate or immersion cooling, and in essence reuse the cooling waste heat over and over again. The concept of energy reuse goes beyond that. It basically, once you use this cascade energy, the possibility of taking the waste heat from the data center entirely, the waste heat ends up being a much higher quality and a much higher grade, and we have many more applications where this can be done. This concept was visualized with ASHRAE, where some years back, where they came up with these cooling classes, W1, W2, W3, W4. Most people are familiar with the airside cooling classifications of ASHRAE, but they have these categories here. And as you look at each one of these, you get to the W5 or the W4 and W5, and those end up being environmentally independent, as illustrated here. The W4 side basically doesn't need any sort of a chiller plant. It's the concept there that you have temperatures, you're using the hottest outside liquid is sufficient to cool your IT. And with W5, you're going even beyond that, and you're looking at the concept of taking that elevated temperature and using that for building reheat or building energy use.
Yeah, so what this slide's showing is actually the use of heat where temperatures are higher with this sort of technology, which means that we don't have to cool as much. So as you can see on the drawings here, where we've got where the output temperature is quite high, but the actual input temperature back into the racks doesn't need to be that much lower. So what this is actually showing is the fact that we're actually using temperatures in a lot better way and a lot more energy efficient. So if you think of your heating at home, if you imagine when you turn the heating on to get yourself warm, as you go the temperature higher each time you lift it, then the costs obviously go up. So the data center is the inverse of that, where the more cooling we have to go in there, the costs go higher. So we can actually run racks within a higher temperature range. It means that effectively the cost of cooling is minimized. What it also means, more importantly, is the fact that these sort of temperatures are actually getting to the point where they're starting to become useful for heat recovery. So once you start going 45 degrees up to 60 degrees, you're in the view where you've got underfloor heating and you've got building comfort heating. So it allows the fact that you're getting the reuse a lot easier out of this high density solution.
Fantastic. So in summary, what you're looking at here, a very simplified path for cooling. In essence, it just falls down to coming up with a reliable distribution solution, kind of re-illustrating a concept that Tim introduced yesterday, this concept of cascade cooling. And here we have some numbers that line up with Tim's discussion of yesterday. Tim, you want to walk through this just a little bit?
Yeah, so what we talked about cascade cooling, if you think of the original slide you just saw before, it was all about the fact that once you get the temperatures higher, it's a lot more usable and uses less cooling requirements, so you're saving the cooling amount. What we're showing here is the fact that actually you could actually run some lower grade heating, but actually cascade it into some of this new technology. So you go back with the view that it allows you to run things like the rear door temperatures at lower supply and returns. But the important thing is that return heat can actually be the supply heat for the next thing on the chain. So what we're saying is the liquids, as we saw earlier, can take a lot higher temperatures. So the actual return temperatures from the early sort of technologies become the new input temperatures. You start to cascade this all together and you get to the top of the row where you get really nice usable heat again.
Fantastic. So kind of going through one thing I want to cover very quickly, and I do apologize, we're running through a lot of complex topics and a lot of complex slides very quickly because of the time constraints, but this will be available for people as a reference if they want to look at it. And the concept of PUE versus energy reuse. One of the things, because I was involved with the green grid years ago, I recall the introduction of power usage effectiveness. And at the time, there was no intent that it included energy reuse. There was a separate category called energy reuse effectiveness. And so is it possible to get a PUE of less than 1? Absolutely not. But is it possible to actually have an energy reuse factor that motivates people to look at the whole energy perspective? Yes, that exists. We're not going to dive into it too much, but the structure of trying to add energy or measure energy reuse is not a new concept, and it's something that needs to be advanced in the industry. It may not be OCP's responsibility to do that, however. So let's kind of look at the key challenge that we're really driving toward today. We've seen a lot of benefits to liquid cooling of data centers, and the key challenge we're seeing in many cases is just how do you plug it in? Everyone understands how to plug in electrical, and that's issue's been solved. And air distribution, that's been focused on. But as we look at the diversity of liquid cooling, we OCP, if we want to inherit that requirement, we need to recommend or make recommendations on ways to install liquids in data centers that are adaptable, that are rapid, simple to align, that can be designed or reference designed with precision, and most importantly, that meet mission critical performance. Here's an illustration of a digital stream compression that we're seeing in the marketplace today. One thing that is very timely with the launch of liquids is the fact that advancement in BIM design has gotten to the point where you can take a sketch, you can translate it into a BIM drawing, and that BIM drawing can very quickly be broken down, in this case, into a series of coupling products that can be shipped out as a bill of materials and delivered in a very lean, compressed fashion anywhere in the world. One of the key challenges that has faced the liquid distribution industry is alignment. With rigid pipes, if you don't, and your flanges, any misalignment ends up becoming pipe stress, people stress, a lot of stress. Coupling-based solutions may end up being a way that OCP would want to look at looking at that, because coupling-based solutions, in their very nature, they accommodate a contraction, expansion, and alignment issues, or at least ones that are designed to do that can actually achieve those goals in an engineered fashion. Years ago, these slides would have been heresy. Back in the 2000 to 2010, the concept of running pipes in a operating business data center was something to be avoided. Now what we see on the left side here, this actually is a colo data center that put clear floor tiles because they're advertising the adaptability of their data center. It's an air-cooled data center, and they added liquid cooling in that data center, and they're showing off that capability. And likewise, one of the things you wouldn't have seen in the past, but because of advancements in mission-critical coupling deployment and understanding, people are now confidently running pipes in their data center on a slab floor, and that's going to be a fundamental. That confidence that you can actually run pipes in an operating data center is fundamental to the concept behind liquid cooling. So where does this concept of mission critical come from? Well, part of the reason I'm giving this presentation is one time I lived inside a welded pipe, and the religion, I was a QA officer on board the USS Bluefish, and we had a religion of mission critical that called subsafe, and that started, unfortunately, with the loss of the USS Thresher back in 1963. 129 people perished because of what started out as initiated as a pipe failure, resulted in a cascading series of events. But the observation from Admiral Rickover was profound, that the loss of the Thresher should not be viewed solely as the result of a failure of a specific braze, weld, or component, but rather considered the consequence of philosophy of design, construction, and inspection. And from his observations came these three pillars of mission critical: holistic engineering, vertically integrated quality control, and certified inspection. When we put together any solution, especially pipe solutions that align with those three pillars, we actually are able to achieve reliabilities that exceed 30 years. And that is what the data center industry has or needs, And when you combine those with the business model requirements that we spoke about, the combination of the two ends up being something that OCP would probably want to take a look at. Is this where part of going to be our recommendation for the future? As we look at these three pillars in greater detail, pillar number one, holistic engineered design. What does that mean? In this case, we're looking at couplings as being, from their business model perspective, because they are adaptable, because they require less skill set, less man hours to install, and they can very easily line up with a BIM reference design deployed model. You'd be looking at the coupling design not only puts together pipe, but it can be engineered, or at least mission critical couplings can be engineered and measured for seismic performance, for expansion contraction performance, for vibration response, reduction analysis, and temperature and pressure and liquid types. Rather than just say that groove coupling is good or bad, the answer ends up being groove coupling when it's designed for holistic engineering applications, that has to, and mission critical applications, that is key. Vertically integrated quality control. On board a ship, after subsafe, every component we had that was subsafe or mission critical rated was traceable back to date and place of manufacture. We knew the heritage of every welder. We knew the traceability. And that aspect, the ability to know that if there ever was a failure, we could trace it back to the date and place, and we could make sure that failure never happened again. That became a foundation of subsafe. And finally, the certified inspection and installation for mission critical solutions with welds prior to the thresher. Only 10% to 20% of the brazes and welds were inspected. After the thresher, 100% inspection went forward. Today, there are mission critical coupling solutions that are designed for a very simple inspection, that a simple visual inspection can guarantee proper performance for 30 years. So as we look at these, rather than specify a particular company's name, obviously I work for Victaulic, but looking at the concept of mission critical couplings as a technology that could be used for optimization of liquid distribution of data centers is where we want to go with that. And so kind of in summary here, as we're drawing to the end of our time, two key recommended actions and timelines. One was to work with the Open Compute project and come up with an acceptable, agreed upon mission critical grade standard for liquid distribution and coupling technologies. Optimistically doing that by June or July. This probably July would be a better number. And then the other aspect, kind of tying into what Tim has been talking about, I think that the goal of integrating energy reuse into Open Compute projects or goals is something that we want to shoot for, but it may be a little bit further off toward December. Tim, I kind of took and ran with this. Is there anything else you would like to add?
Yeah, I think the one thing, certainly from the last presentation, it's all about lessons learned. I think the lessons learned is the fact that heat exchangers are relatively simple things. The crucial bit is making sure they're connected together. Connected together with the right specifications is really crucial to making a modern style data center.
Well, thank you for that. I think we still have a couple minutes left for Q&A. Would love to hear any questions or concerns people have, and look forward to working with you on meeting these goals. Thank you.
So, am I live?
Yep.
Okay. So first off, I'd like to thank everyone for today's presentation. This is Don Mitchell live. For some reason, Tim has had a hard time coming in. We recorded this with an expectation of a requirement of 20 minutes, and so we did it very compressed. We actually wrote this presentation with an expectation of it being kind of a group chat. Some of the key things I wanted to get out of this more than anything else is an encouragement for OCP to focus on the areas that OCP could own versus replicating what others are already doing. For example, ASHRAE and TC 9.9 already are set up some guidance, and we need to work with them closely and let them continue to provide that guidance on the parameters and the definitions of liquid. But the area that was being suggested for OCP And what I'm looking at trying to do is to help OCP define what is mission critical as we look at the distribution in the data center facilities team. And so with that, if there's anyone that would like to share in that or join in that committee, that was the original purpose of this presentation. If you guys, looking at the chat screen, if there's anyone that wants to make a comment at this point, I'll wait a couple more minutes. Otherwise, we'll drop off. And I hope you enjoyed today's presentation. And thank you, Tim, although I know that for some reason you've had a hard time dialing in.